Let's talk about the crust, the mantle, lithosphere, and asthenosphere. In particular, how we define what those chemical and rheological layers of the Earth are, and where the boundaries between the layers lie. We have some direct evidence of the mantle composition, geological evidence such as ophiolites. So these are pieces of oceanic crust in the uppermost mantle that have been abducted onto the edges of continental crust. And these happen at subduction zones, such as the high-grade rocks and serpentinites, pillow basalts that we have in the Franciscan complex nearby, to larger ophiolite complexes that exist in places like Oman. We have dredge samples from ocean fracture zones. We have pieces of mantle xenoliths that erupt in some basalts or that are found in lower parts of the Sierra Nevada batholith. We have xenolites from Kimberlite volcanoes. These are the diamond-bearing volcanic pipes that form during explosive eruptions in the geologic past and in generally the cratons of all the major continents. And we also have cores from deep ocean drilling. So dunite xenoliths in basalt, these are just carried up within, in this example, Hawaiian basalts. Kimberlite xenoliths can include peridotites that contain chrome diopsides or pyrope garnets and even diamonds from potentially the lower mantle. And they come up in explosive eruptions that I mentioned in a matter of days or perhaps even hours. There are no modern kimberlites, so we don't have examples of these, but that is the best guess. We also have ophiolites, and this is an idealized cross-section of an ophiolite that shows both crustal rocks and mantle rocks that become scraped off onto the edge of continents. They include deep sea sediments at the top of an ophiolite sequence, pillow basalts, and sheeted dikes near to the top of the volcanic sequence. Lower down, there are layered or isotropic gabbros at the base of that lower oceanic crust, and ultramafic rocks that are the uppermost part of the mantle that are sometimes exposed in these ophiolites. And the largest one and the most complete ophiolite sequences in Oman, where, like some of the rocks in the Franciscan complex, these oceanic crust and upper mantle rocks are exposed with high-grade rocks and other metamorphic rocks from this thrust sheet that was abducted onto the edge of that continent. Now we have two kinds of layering that we can refer to when we're talking about the structure of the Earth. Those can be a rheologic layering that includes the lithosphere, asthenosphere, lower mantle, and the core, or that can be a seismic or a compositional, a chemical layering in the Earth that includes the crust, the mantle, and the inner and outer core. Now, in terms of rheology, what I mean are, this is a thermomechanical layering, so a rigid outer crust that is the lithosphere. So that includes the crust and the uppermost mantle, and comprises the tectonic plates. A plastic and deforming asthenospheric layer that underlies the lithosphere and that the tectonic plates ride on because it's deforming, because it has a small amount of partial melt. And then the lowermost mantle that is solid, a liquid outer core and a solid inner core. Those are separate classifications of those layers of the earth, and it's based solely on rheology. Whereas the chemical layering or the seismic layering that we see in the crust, the mantle, and the core is based on the chemistry of those different layers. So differing chemistry of continental versus oceanic crust. More uniform chemistry in the mantle, but there are zonations that we'll discuss in terms of depleted or fertile mantle. And then, of course, the core. And we can look at the different properties of these layers, and specifically the differences between a thicker continental crust versus a thin oceanic crust. And that corresponds to a thicker continental lithosphere versus a thin oceanic lithosphere that thins down to almost nothing at spreading centers. Now, I also want to point out the transition zone that's shown here between about 410 and 670 kilometers depth. That transition zone is referring to the phase transitions going on in the mantle at those depths. And so we see here the depth profile in the mantle. So we have depth increasing down on the left, and this is density on the x-axis. And what's happening between about 410 and 670 kilometers depth is that we see changes in the mineral structures that also affect the seismic properties within the mantle, because the densities of those phases are increasing as they transform to smaller volume, denser crystal structures with the increasing pressure. Now, the crust is the outermost layer of Earth's three compositionally distinct layers. That's the crust, the mantle, and the core. And it's separated from the mantle by the seismically well-defined increase in seismic velocities, and those are the P waves, and that boundary is the MOHO discontinuity. It's a picture of Andrea Mohorovičić. It was he was that after a severe earthquake in 1901 in Croatia that studied the seismic stations that they had set up in Zagreb not far away, that led them to identify the MOHO and the fact that this different layer within the earth, the mantle, existed. These are the travel time plots for that earthquake that Mr. MOHO plotted up. And these show a P wave here and a PN wave here that are the different P waves that are generated at an earthquake from an earthquake focus. The P waves are those that travel through the crust. The PN waves are those that actually travel through the mantle. And what he noticed was that there's an overlap between about 300 and 720 kilometers, so this area here, where there were two waves. One that was, he identified the P wave that was traveling at about 6 kilometers per second, and the PN wave that was 8 kilometers per second, and realized that this corresponded to a change in the velocities. This is depth versus velocity here. There's a change in velocity at about 47 kilometers depth. And it was from this that he identified that there was a different density layer in the Earth that started at about that depth, and thus identified the MOHO. So he concluded that at about 50 kilometers depth, there has to be an abrupt change in the material that comprises the Earth, and that was because he saw a change in this the velocity of the earthquake waves. But it wasn't accepted immediately. And in fact, it was later confirmed by Gutenberg in 1915. So we see that the MOHO separates the mantle from the crust, and that there are two fundamentally different types of crust, the continental and the oceanic. And then early on, the lithosphere was synonymous with the crust, but now it's used as including both the crust and the uppermost mantle. So prior to that, and even for 50 years after this discovery of MOHOs, crust was just used as a strong outer shell of the Earth, and it wasn't distinct from the lithosphere. And in fact, there's a well-known geophysicist at Stanford, Norm Sleep, who submitted his first paper for publication in the Geological Society of America Bulletin. It was in 1967. It was actually sent back to him with a note from the editor saying, please use only crust or lithosphere because they're synonymous. So 1967 may seem like a long time ago to some of you, but it wasn't really that long ago. And this is about the time that plate tectonics was still a new thing, and we're still defining these chemical and rheological layers within the Earth. So even as these ideas evolved about the crust becoming more mafic with depth, so it's stratified according to density, it was uncertain whether the MOHO was a chemical change, so from mafic rocks to ultramafic rocks or peridotite that makes up most of the mantle, or if it was an isochemical phase change, so going from a gabbro to an eclogite, so metamorphosing a gabbro to a denser rock type, an eclogite, but being chemically the same. And one thing that comes up is that eclogite and peridotite, so eclogites in the lowermost crust and peridotites in the mantle, have very similar densities, and they have very similar PNS seismic velocities. And that means that they're difficult to distinguish based on seismic techniques. So heat flow coupled with crustal thickness measurements, and the first measurements of seismic anisotropy in the oceans confirmed this widespread feature that is the MOHO as a chemical boundary, and it was in the 60s and the 70s. And so crust is this thin layer of a distinctive chemical composition from the underlying upper mantle. Continental crust has an overall composition that is andesitic, so something about 60% silica. Oceanic crust is basaltic, and so it's less silica rich, somewhere between 45 and 50% silica. And the mantle and the lowermost lithosphere and the asthenosphere have an ultramafic or pretatitic composition at 45% silica. So there's some uncertainty. There's probably a small proportion of eclogite that is a basaltic composition that's included within that. But these are simplifications. We look at the oceanic crust. It is, we look at just an example of a spreading ridge. What we know about the structure of the oceanic crust is based on what we see in ophiolites. And I used the example of the Oman ophiolite before. But that is how we understand the petrologic changes that we see as we move from the top of the oceanic crust down into the uppermost mantle. We also have evidence from the deep sea drilling program. These red lines correspond to where parts of the oceanic crust where we've drilled through to sample these rocks. And drill hole 504B is actually the East Pacific Rise, and that's drilled from the spreading center down through the uppermost lavas, the sheeted dikes, and elsewhere we've drilled down into the isotropic gabbros and different parts of that oceanic crust. And so that's how another way that we're developing this model for the idealized ophiolite and correlating that to actual oceanic crust. And we see also changes in densities of the rocks depending on the age of the oceanic crust. So the young oceanic crust near the ridge, recent to 3 million year old oceanic crust to greater than 50 million year old oceanic crust. And the differences are in part because as we move away from the ridge, the rocks are becoming colder, becoming more dense, and have faster seismic velocities. And you can see that in these plots where at 12, let's use something higher, at 8 kilometers depth, we're seeing velocities change from something just below 8 kilometers per second to a little bit faster to just about 8 kilometers per second. So small changes, but those densities do correspond to increased seismic velocities. So from this idealized ophiolite model, we can look at what we can see at various exposures of ophiolitic material at the Samael ophiolite, the Bay of Islands, and Troodos ophiolites. They're at the base of the oceanic crustal rocks. We see a difference between a seismologic moho and a petrologic moho. And the difference arises because the densities of the rocks at the base of the oceanic crust are similar enough to the underlying mantle rocks that they're indistinguishable. And so if we were looking at a reflection profile through any of these ophiolites, you would draw the moho along this seismological moho line. In reality, when we're considering differences between crust and mantle, it's the compositional differences that are important, and that's this petrologic moho. So the rocks don't actually become ultramafic and pretatitic until below that seismologic moho. And so that's really the true moho if you're considering compositional differences. Now, if we consider differences between the oceanic crust and continental crust, oceanic crust is quite a bit thinner than continental crust on the average. It is basaltic, so less silica rich compared to an andesitic continental crust. Oceanic crust is never going to be more than 170 million years old because ultimately it's subducted, and that's the end of that. The continents, however, are long lived and have been around for somewhere around 4 billion years. And they're arising from different tectonic processes. The oceanic crust, in general, from seafloor spreading, whereas the continents are a result of arc magmatism and accretion of other material, whether it's continental, oceanic crust that ends up creating continents. And the topography that we see in the ocean basins is really a function of age, versus in the continental crust where it's the tectonics that influence whether we have low points as basins or high mountains. And this thinner, denser oceanic crust is also going to have isostatic effects, and so sit lower on the underlying asthenosphere compared to the continental crust that is much thicker and less dense, and so sits higher on the asthenosphere. Now, there are different kinds of continental crustal provinces that we can consider, and those include the shields and the platforms that are the older cores of the continents. There may be large igneous provinces or large basins where there are foredeeps or parts of cratons. We can have extended crust in continental rifts, either a rifted continental margin or a rift such as the Basin Range. Or we might have orogens, so island arc or continental arcs, forearc. And these provinces are any large area region that's considered, that's characterized by similar features or by a history that's differing from adjacent areas. Now, to define some of these terms, craton, shield, and platform are used together often, and they have subtle differences. A craton is the ancient crust that's been stable for a long time. It's comprised of igneous and metamorphic rocks, so the cores of the continents. Shield is any part of the craton that's actually exposed, and a platform is a craton that's been overlain by younger sedimentary rocks. And so if we just look at North America, you'll see the shield here south of Hudson Bay, the craton north of there, and the platform surrounding the craton and the shield. So the sediments overlying this older core of North American continent. A map of world geologic provinces could include other shield areas, like I just showed for North America. And those could include the shield of the South American continent, Scandinavia, Australia, India, and Africa, different parts of the shield exposed there. And then surrounding that, these pink areas are the platform with sediments covering those ancient shields. And those are all surrounded by The origins, the Aleutians, the Cordillera, the Andean origins, the origins in the South Pacific area along Japan, in the Mediterranean, and along the Alpine Himalayan belt. There are also basins shown inland of those origins in Western North America, Western South America, and basins in interior Africa and Europe, and the Arabian Shield. There are also some large igneous provinces shown, flood basalts in the Pacific Northwest, the Deccan Traps in India, those in Eastern African Rift, the Siberian Traps, and there's extended crust. So the Basin and Range in western U.S., extended crust along the margins of the Atlantic that were opened up when Pangea split, extended crust in Argentina, surrounding the Western Pacific, and in the South Pacific as well. So an origin or an orogenic belt or orogenies are episodes of crustal deformation that generate new crust and mountains. Cratons are not affected by younger orogenies. Orogenic belts are these elongate belts that have high relief, high topography, and are deformed, and generally form mountain chains like the Andes or the Aleutian Arc. Origins are crustal tracts that were deformed at about the same time. Those can include extensional origins like the Basin and Range. Should look at crustal thicknesses too globally. And this map shows areas where of note are where continental crust is thicker than 50 kilometers. It's relatively rare, but beneath Greenland, the Himalaya, Antarctica, and the Cordillera, those are areas that where we've got deep crustal roots, and they account for less than 10% of all the continental crust. Looking at other provinces, including shields, platforms, extended areas, and basins and other LIPs, we see crustal thicknesses, and we'll just look at the bulk of the crustal, the mean crustal thicknesses. For shields, it's somewhere around 40 kilometers thick. Platforms, a little bit thicker, so shield plus some sediments. Extended crust is quite a bit thinner at about 30 kilometers. Basins, variable, somewhere between 40 and 50 kilometers thick. Large igneous provinces, also variable, can be quite thin, in fact, from 20 to about 45 kilometers thick. And then origins, extremely variable. If you're including mountain belts like the Andes and the Himalaya, you'll have crustal thicknesses somewhere around 70, even up to 80 kilometers thick. And then they range from 30 to 60 kilometers in more average origins. Let's look at some different parts of North America, including the Canadian Shield, the Great Plains, the Cordillera and Rocky Mountains, the Basin and Range Province, the Appalachians, if we consider those in terms of seismic velocity, just looking at the P waves, what you'll see on this diagram is the faster P waves down here from 6.5 to 7.5 kilometers a second, to very slow P waves down here in purples. What you'll see is that, for the most part, the Canadian Shield and the basins surrounding the shield, the northern parts of the Appalachians, those are all higher velocity parts of North America, corresponding to older and generally denser crust, whereas the areas of continental rifting and the basin and range have lower seismic velocities, and those are corresponding to less dense rocks, younger intrusions, and so you get the slower velocities that correspond to that. If we look at different parts of California and just the evolution of the westernmost part of the U.S., you'll see, if we just look at the geology first, you'll see the Sierra Nevada in red and the remnants of the southern Sierra Nevada in Southern California. And those are from the Mesozoic arc, before we had the San Andreas. This was the volcanic arc that was generated from the subduction of the Farallon plate. We have younger volcanics and other intrusive rocks related to the Cordillera, and these are the southernmost part of where the volcanism the magmatism is taking place from the existing subduction of the Juan de Fuca plate beneath western North America. And we have the Great Valley in the center, that is the basin generated from bending in front of the arc. We have these greenish rocks of the Franciscan complex. So these are generally metamorphic rocks, low-grade rocks and sediments associated with ophiolitic material and other accreted material onto the edge of the continent, also related to the Mesozoic arc. And then back here in the Mojave Desert and Death Valley area, this is the part of California that is within the continental rift of the Basin Range, so some spreading and thinning of the crust there. You can see the corresponding topography in terms of the white colors representing the high topography of the Sierra Nevada, the coastal ranges that are related to the accreted terrains, as well as uplift along the strike slope faults that run along the western part of California. You can see the Great Valley, the basin in between the two. You can see the ridges and valleys of the Basin and Range province that are in eastern and southern California. If we look at a cross-section just south of San Francisco and just south of the Mendocino Triple Junction, so this, I suppose, you know what, I'm going to go back and show you where the San Andreas Fault is on this diagram so that we can talk about the Mendocino Triple Junction, because we haven't yet. The San Andreas comes out of the Gulf of California into beneath the Salton Sea, runs east of LA. There's a bend in the fault as it follows north of Los Angeles. It comes north east of Santa Barbara, east of Monterey Bay, through San Francisco, just to the west of San Francisco, goes offshore to where the epicenter for the 1906 quake was, comes back onshore and separates Point Reyes National Park from the rest of the bay, North Bay. And then it runs along the coast, clipping the coastal areas, and then goes offshore around Mendocino. Mendocino is this point right in here in California. So the Mendocino Triple Junction is where the San Andreas Fault encounters the ridge behind the subducting Juan de Fuca plate that is generating the volcanism starting in northernmost California and into Oregon and Washington to the north. So that's the triple junction there. So the cross section that I'll be showing you is in Northern California, and then I'll show you one further south of San Francisco. Now here we go. So this is the cross section just south of San Francisco. We have relics of the subducted oceanic crust, the San Andreas Fault that looks to me like it's further east than where it's marked, the selenium block, which is the offset part of Southern Californian rocks that were brought north along the San Andreas Fault. The Calaveras Fault is another near vertical structure that is also a right lateral strike subfault, also accommodating plate motions between the Pacific Plate and the North American Plate. If we look at the cross-section just south of the Mendocino Triple Junction, you'll see the San Andreas Fault offshore, the coastline, and then some other faults further inland. And you'll see reflectors that show the structures that are residing beneath the upper middle crust and that are defining the base of the North American crust and the top of that old subducted oceanic crust. Here we go looking at the Mendocino Triple Junction. So here's the San Andreas Fault coming out of the Salton Sea, coming north through San Francisco, Point Reyes, just offshore, and then to the Mendocino Triple Junction. We have several, these are seismic velocity models for the Mendocino area. And what you're seeing is fast velocities in the purple color corresponding to oceanic crust, underplating, Western California. There are also low seismic velocities under Great Valley sediments in yellow. The Franciscan complex rocks are in green and represent more intermediate seismic velocities. And then there's material in pink that represents Sierra Nevada material that's related to those plutonic rocks beneath the Sierra Nevada. And if we compare cross sections of what the Western Plate boundary looked like in the Mesozoic, so while subduction was taking place, you'll see that we have this descending Farallon Plate of oceanic crust subducting beneath Western North America under what is now California, an active arc that is the Sierra Nevada arc that was generated where fluids being driven off the descending Farallon Plate generated melting that fed the volcanic arc. The magmatic rocks that never reached the surface crystallized to form the granites of the Sierra Nevada. Otherwise, they were erupted into the volcanic rocks that are preserved in eastern California. We also have the Great Basin, this four-arc basin that's formed from flexure during subduction, and the Franciscan subduction complex, which comprises both sediments scraped off the subducting oceanic crust, as well as rocks that were part of the subducting Farallon plate that were actually exhumed and are now part of that Franciscan complex. Compare that to the modern cross-section that looks like this, where we have exposed granites in the Sierra Nevada, where those rocks were uplifted and the material on top was eroded off. Those were in part uplifted along normal faults that are bounding the ranges in the Basin and Range, that crustal rift zone. We have this remnant oceanic crust underplating everything, including oceanic crust beneath the Great Valley, that's part of a period when the subducting Farallon plate retreated and took a step back during the Mesozoic. And we have the coast ranges that are comprised of the Franciscan rocks and that are uplifted in large part along these strike-slip faults, the Coast Range thrust, the Hayward Fault, Calaveras Fault, the San Andreas Fault. All of those are acting together to actually uplift the coastal ranges and to give us the modern topography that we have here. Now we also have some continental scientific drilling that takes place, the Kola Peninsula in Russia and the KTB borehole in Germany. And those give us an idea of the structure of the continental crust. They've reached down about 9 kilometers, at least the KTB drill hole has. And it's given us information about the rocks in the brittle upper crust and starting to reach into the mid-crustal regions. But there's a long way to go to get from where that drill hole is today down into the lower crust that is infrequently exposed on land where we can study it, and certainly a long way from the continental moho. If we look at the P wave velocities in the mantle, so below the moho, under North America, we see again faster velocities beneath the shield and the platform compared to beneath the Basin and Range. It's again reflecting there's colder mantle beneath the older parts of the continent and warmer and thus slower seismic velocity mantle beneath the younger and extended Western North America beneath the Basin and Range. So we have different mohos, the petrologic and the seismic mohos, and some other definitions that we won't go into here. And we have a cross-mantle boundary. To a purist or to a geophysicist who's thinking purely about geophysics, the moho is simply an abrupt jump in the seismic P wave velocity to above about 7.6 kilometers per second, or the depth that corresponds to that velocity increase. And that's a definition remnant from the late 60s. Mohos often used where one actually means cross-mantle boundary, and cross-mantle boundary is often a more appropriate choice of terms instead of moho in those cases. And I'm going to define the crust-mantle boundary as the boundary between the peridotitic mantle material in the upper mantle and the crust that also includes the eclogitic lower crust, if the lower crust is eclogitic at any given point. So we can do some thought experiments. What happens to a crust-mantle boundary in a subduction zone? And what happens to the moho in a subduction zone in the forearc area? We look at a diagram with those two same thought experiments at the top and just look at a subduction zone and back arc basin. The crust-mantle boundary, to me, looks fairly straightforward to define. The crust-mantle boundary defines the petrologic region between the mantle and the crust. There, here. It includes the oceanic crust, which is much thinner. So this is all crustal material. It becomes trickier at depth. Where does that crust-mantle boundary go if we're subducting crust? Well, then it may come to a point where we have to consider the seismic velocities in order to find that crust-mantle boundary. Now, if we're talking about a moho, the moho is, we can look toward the crust-mantle boundary, but again, in this region beneath the arc in a subduction zone and above that subducting plate, it becomes a little fuzzy. From a geophysicist perspective, if we look at a subduction zone, and the subduction zone has the opposite polarity, so we have subduction dipping to the right here. The moho looks like a prominent reflection in this seismic profile. So it is this line here beneath the crust. And when you get to the subduction zone, what you see is the subducting crust being defined by a separate moho. So you see the subduction zone and a mantle wedge in here. So to the reflection seismologist, that red line is the moho. If you're a petrologist, then the difference is simply that change from going from the mafic lower crust, in this case we're looking at oceanic crust again, but looking at mafic lower crust, I'm looking here. So we're following the mafic rocks at the base of the oceanic crust. That's approximate. And then the rocks beneath that are Harzburgites, peridotites that make up the mantle. So it is a compositional difference in terms of the amount of silica and other elements that characterize the mantle versus crustal rocks. Beneath a continent, this could involve, instead of a mafic lower crust, an eclogitized lower crust compared to peridotites in the mantle. And in that case, a seismologist would draw the moho much higher because the seismologic moho would simply look at those reflectors or the seismic velocities, and eclogite would look indistinguishable from the peridotic mantle below. So how do we make continental crust? Above subduction zones, fluids are driven off the subduction zones. They enter the mantle wedge that it overrides it. It triggers melting by lowering the melting point of the peridotite and the mantle wedge. And we're not talking about melting the subduction slab, because that's only a rare occurrence. It is the mantle wedge that's melting. And the magma that's generated is a partial melt of the mantle, and that's a basaltic composition. Above plumes, so this might be in oceanic plateau or underplating in the continents, a plume like a hotspot like Hawaii and volcanism that you see there, like the mid-ocean ridges, you're seeing decompression melting. It's a different process. You also get basalt, but you're reducing the pressure on the underlying mantle and producing, again, a partial melt of the mantle and generating a basalt. So different processes, same result. If we consider how fast continental crust is growing, we have to have a mass balance between the crust that is being recycled into the mantle at subduction zones and the crust that is being generated by volcanism, magmatism at arcs and at mantle plumes and at mid-ocean ridges. And it has to balance. We have additions above subduction zones on the order of 2.5 cubic kilometers per year. To a smaller degree, additions above plumes and other mantle upwellings. But we also have losses at subduction zones, whether they're oceanic or continental subduction zones. And we have losses from the continental crust by delaminating the lower crust. That is where you have a mountain belt with a deep crustal root. If that crustal root becomes eclogitized, or there's some other structural reason why it is unstable, that eclogitized lower crustal root can delaminate and actually fall into the mantle. We're talking geologic rates. But you're going to have crustal removal of that crustal root by delamination from a variety of hypothetical processes. But you'll see, on the whole of things, these additions and these losses balance out. Okay, so we've got the production of continental crust equal to the modern volume of continental crust over long periods of times. They have to be balanced by subduction losses. The processes have changed over the course of the history of the Earth. But after the continents were formed, the processes are generally balancing such that the masses are not significantly changing, and we have growth and recycling processes ongoing to balance one another out. If we look at the rate of continental growth over time, and this is based on a variety of data, but including isotopic data and considerations of subduction rates and ages of the crust, you can see that there are a variety of estimates here, but we have the relative volume of the continental crust and the age from the earliest part of Earth's history to today. And what you see is that in general, that after about 3.5 million years, the volume of continental crust has stabilized. There are some estimates that are somewhat younger, maybe 2.5 billion years. But for a very long period in Earth's history, from this period and onwards, we have a stable volume of continental crust, and the processes that are maintaining that stable volume of continental crust. So what kind of continental crust is growing today? Above subduction zones, the primary magma is basalt, that partial melt of the mantle wedge above the subducting slab. Above plumes, again, from decompression melting, the primary magma is basalt. But average continental crust is andesitic. It's much significantly more silica-rich than basalt, so 60% compared to about 50%. So what's happening? First, we have crustal formation mechanisms and compositions that were different in the earliest part of Earth's history. Most of the crust formed then, but in those cratonal areas and somewhat younger terrains, 3-4 billion year old terrains, are not terribly different. Intracrustal differentiation leaves a dense lower crust that can become eclogitic and can delaminate during arc formation or accretion of different terrains or continental collision. And we see something that looks like that beneath the Sierra Nevada today. There is chemical weathering of surface rocks that leads to depletion of magnesium, and subduction of shales can remove a mafic component of the crust. And the moho is not the crust mantle boundary, and ultramafic and eclogitic crust is often mistakenly ascribed by seismologists to the upper mantle. But we also know that from xenoliths, that eclogites are only a small percentage of the cratonal roots. So, whereas continental crust is andesitic, about 60% silica, the mantle is 45% silica. It's dominantly peridotite, that's olivine and orthopyroxene, with maybe some clinopyroxene, a tiny amount of plagioclase, maybe some spinel and garnet. There are different kinds of mantle, although I say this with some hesitancy because overall the mantle is very similar in terms of the major element distribution. If we consider 3 different types: a fertile mantle, oceanic mantle, and a low temperature craton, so an old craton. Broadly, the chemistries are similar. Magnesium differs somewhat. And we can refer to different parts of the mantle as being fertile versus depleted, and that refers to the degree to which mantle has been modified by extraction of partial melt. So I refer to that when I talked about extraction of partial melts in the mantle wedge beneath arcs and beneath above mantle plumes or beneath ocean ridges. So high magnesium in depleted cratonic mantle represents multiple melting events. That leads to lower density than a fertile mantle or the oceanic mantle. And that will result in more orthopyroxene, so it's generally stronger, resistant to smaller scale convection and delamination that would otherwise remove the deepest lithosphere that is nearly the same temperature as the ionosphere. Enriched mantle is the opposite of depleted. Sometimes the reference state is more of a mid-ocean ridge basalt, and sometimes the bulk silicate earth or chondrites. Some ocean island basalts and continental flood basalts come from enriched mantle. That refers to the trace element and the isotopic characteristics, again, not the major elements. A fertile mantle refers to the major elements such as calcium, aluminum, and sodium. The mid-ocean ridge basalt source is a fertile source, and that can provide basalt by partial melting, but it's depleted, so those basalts are low in some of these trace elements. The Archean sections of continents are underlain by mantle that has compositional buoyancy that results in a high viscosity and a buoyant raft for the overlying crust. The upper part of the lithospheric mantle, so this is the uppermost mantle that is part of the lithosphere, is denser than a ionosphere because it's colder, but the lower part is warmer and nearly at asthenospheric temperatures, so is less dense than the asthenosphere. Again, it's high magnesium, more orthopyroxene, it's stronger and resistant to that convection again. Now, continental mantle helps in the long-term survival of continental crust, but oceanic mantle helps in the destruction of oceanic crust. So as an oceanic plate ages, oceanic lithosphere cools and thickens so that at some point it becomes gravitationally unstable and subducts. So gravitationally, we're talking about density differences. In contrast, the Archean sections of the continent are underlain by mantle that has experienced high degrees of partial melting and melt removal, including removal of water. That induces a compositional buoyancy that results in a high viscosity and a buoyant raft for the overlying crust, and that allows it to survive for 4 billion years. Now, if we consider the age of the mantle lithosphere, this is a rhenium osmium plot that shows the differences between a fertile mantle and depleted mantle. This bottom left quadrant represents single stage melt depletion, and these lines, these tie lines, represent 1, 2, 3, and 4 billion year ages for the mantle lithosphere. If you notice, the cratonic areas are generally depleted, and older parts of the mantle lithosphere, particularly compared to arcs up here that are younger and more enriched. Now, to the first order of things, the lithosphere is equivalent to the tectonic plates because the plates form the rigid outer crust of the Earth and are riding on that plastic asthenosphere that underlies the lithosphere. But there are some aspects where the lithosphere is not equivalent to a tectonic plate. The plate is the part of the crust and upper mantle that translates coherently during the course of plate tectonic motions. The thickness of the plate can be controlled by chemical or buoyancy or by stress, and as well as temperature. But there's no way to measure its thickness, and the plates are ephemeral. They're changing over the course of plate tectonics. Now, the lithosphere is the rigid outer layer of the Earth that's required for plate tectonics to work. It differs from the underlying asthenosphere in terms of its rheology, so its flow properties, rather than its chemical composition. Under the influence of the low intensity or long-term stresses that drive plate motions, the lithosphere responds as a rigid shell, while the asthenosphere is behaving as a very viscous fluid. And the weaker mechanical properties of the asthenosphere are due to the fact that this part of the upper mantle is much hotter. The asthenosphere underlies the lithosphere and provides a weak substrate for the lithosphere to glide on. And the crust is the upper part of the lithosphere, which is mainly composed of mantle. As I pointed out earlier, the lithosphere thins to a few kilometers beneath ocean spreading centers. It thickens to about 100 to 150 kilometers beneath the older parts of the ocean basins, and is up to 250 to 300 kilometers thick under the continents. There's seismological evidence for the lithosphere and the asthenosphere. Plate tectonics requires an outer rigid layer of the Earth, the lithosphere, to decouple from an underlying layer of lower strength, that's the asthenosphere. And the hypothesis that the Earth has an asthenosphere can be tested by searching for a layer with the physical properties that are attributable to its low strength. The presence of this low velocity zone, a seismological low velocity zone in the upper mantle, provides evidence for a low shear modulus, and that's material that's close to its melting temperature, so it's weaker. The low velocity zone is much better developed under the ocean basins than under the continental shields. So oceanic lithosphere is better defined seismologically than the continental lithosphere. That low velocity zone is this zone here between about 100 and 200 kilometers deep. You see that there is where you see an increase in seismic velocity at the Moho, and in general an increase in seismic velocities with depth, that this low velocity zone at 100 to 200 kilometers deep is slower than surrounding regions of the mantle. If we look at S-wave velocities, we see that at 125 kilometers, the continents are well defined by high S-wave velocities, suggesting that the lithosphere is thicker beneath the continents than it is beneath the oceans, where the S-wave velocities are low. At 350 kilometers depth, most of the S-wave velocities are low or at 350 kilometers, we see that generally we have lower S-wave velocities, suggesting that that's near the base or below the depth of the lithosphere. So we're reaching the maximum thickness of the lithosphere at that point. We can look at a definition of the lithosphere from Moores and Twiss that says the top of the mantle is a relatively cold, strong boundary layer called the lithosphere, which includes the crust and upper mantle to a depth of about 100 kilometers under ocean basins and possibly up to 200 or 300 kilometers under continents. Heat escapes through the lithosphere largely by conduction and by transport in upwardly migrating fluids such as igneous melt. The thermal regime of the lithosphere is controlled by conduction. So that's another way to define the lithosphere is an Earth's thermal boundary layer where heat is lost by conduction. And beneath that, heat is transported largely by convection. So if we look at conduction, heat flow Q is proportional to the thermal gradient, which is dT over dz, and proportional to the conductivity of the rocks through which heat is conducting. If heat production is neglected, then the temperature gradient is linear. And so for a 100-kilometer thick lithosphere with 0 degrees Celsius at the surface and 1300 degrees Celsius at its base, you get a thermal gradient of 13 degrees C per kilometer. But the continental crust contains a significant amount of radioactive elements, potassium, uranium, thorium, that produce heat during decay. And so conductive geotherms in the continental crust are steeper, and you get higher geothermal gradients, so greater than 13 degrees Celsius per kilometer. Convection, on the other hand, is approximately adiabatic, such that your thermal gradient is proportional to the temperature over the heat capacity of the materials. And this is about 0.6 degrees Celsius per kilometer in the mantle. If we compare continental and oceanic geotherm, oceanic geotherms and continental geotherms converge at about 200 kilometers depth, so near to the base of the continental lithosphere. There are three definitions of lithosphere. We have a thermal definition of the lithosphere, that is the outer shell of the Earth where there's a conductive temperature gradient overlying a well-mixed adiabatic interior that is controlled by convection. So that equates lithosphere with a thermal boundary layer. The thickness of that thermal boundary layer is generally thicker than the elastic lithosphere, and the lower part of the thermal boundary layer flows readily. Related to that is the definition that the thickness of the lithosphere corresponds to the depth of the 1280 degrees C isotherm, which corresponds to the temperature of melting for mid-ocean ridge basalts. We can have an elastic or a mechanical lithosphere, where the thickness is determined by seeing how the plate bends where it's loaded, such as outboard from trenches, around oceanic volcanoes like Hawaii, or when a load is removed, such as glacial rebound observed in Scandinavia. And the base of the mechanical lithosphere is approximated by the 600 degrees Celsius isotherm, and so is about half the thickness of the thermal lithosphere. Silicates flow readily at high temperatures and high stress, so the lithosphere appears to be thicker at low stress levels and short times than at high stress levels and long times. So the effective elastic lithosphere is thin for long-lived loads, but thick for short time scales. We have a chemical lithosphere. For igneous geochemists, the lithosphere is the part of the upper mantle that doesn't mix and so retains its chemical features established at the time of its formation. And melts generated from this are expected to have a chemical and isotopic feature consistent with potentially very long periods of isolation from convection. So is the asthenospheric mantle. And what this means is that the chemical lithosphere has an isotopic signature that is long-lived and that we can pick up in isotopic ratios from old rocks that have survived many different geologic events. So if we looked at the thermal structure of an old lithosphere, perhaps we would see this kind of layering. The crust at the outermost part of the Earth, a mechanical boundary layer that is the uppermost part of the mantle that's strong and comprises the bottom of the lithosphere, the thermal boundary layer, which equates to the asthenosphere, and a more steady state lower mantle that is again behaving rigidly. Most geoscientists recognize the lithosphere by its seismic characteristics. So it's the high velocity region at the top of the mantle. It generally overlays a low velocity zone, and it starts at an average depth of 40 kilometers under the oceans and starts as deep as 150 kilometers under the cratons. And so even while recognizing that the seismic velocities are varying with the composition, the temperature, the fluid content, this definition is still an imperfect proxy for rheology. But again, if we go back to look at the S-wave velocities at 100 kilometers depth compared to 350 kilometers depth, we see that the continents are well defined at 125 kilometers with the low S-wave velocities, suggesting that those are well within the lithosphere. And at 350 kilometers, we're getting to the bottom or we're below the continental lithosphere.